Hello friends, this is Madan. In previous class, we discussed crystalline allotropic forms of carbon. Today, we are going to discuss another crystalline allotropic form of carbon, that is Buckminster fullerene C60 molecule. What is meant by crystalline allotropic form of carbon? Crystalline allotropic form means constituent particles are arranged perfectly order. Constituent particles perfectly orderly arranged. Perfect order of arrangement takes place in the solid. That perfectly ordered arrangement of constituent particles containing solid is called as crystalline solid. Now amorphous means disorder arrangement, not perfect arrangement. Disorder arrangement of constituent particles takes place in amorphous allotropic form. Today we are going to discuss Buckminster fullerene C60 molecules. Fullerenes all are molecules. Fullerenes all are molecules. Example C60, C120, C180. Fullerenes all are in these fullerenes, molecules are arranged with each other. Molecules are combined with each other to form hollow spheres or ellipsoid or tube. Spherical solid fullerenes all are called as buckyballs. Spherical solid fullerenes all are called buckyballs. Example C60, C120, C180, etc. Fullerenes all are aromatic in nature. Fullerenes all are aromatic compounds. They have aromaticity. Buckminster fullerene C60 molecule is also called fullerene or buckyball. The structure of C60 molecule is similar to soccer ball structure. Buckminster fullerene consists of number of C60 molecules. Each C60 molecule, Buckminster fullerene, is a hollow sphere. Buckminster fullerene C60 molecule is a hollow sphere. In this C60 molecule, pentagonal rings and hexagonal rings are arranged alternately. C60 molecule contains 12 pentagonal rings and 20 hexagonal rings, each pentagonal ring surrounded by hexagonal rings. Similarly, each hexagonal ring surrounded by pentagonal rings. They are arranged alternately. Here, carbon atoms are common properties of both pentagonal rings and hexagonal rings. Each carbon is sp2 hybridized. Each carbon forms 3 sigma bonds with other carbon atoms. Each carbon forms 3 sigma bonds with other 3 carbon atoms. Each carbon has one unpaired electron in pure pz orbital. Each carbon carries unpaired electron. Due to the presence of unpaired electron, Buckminster fullerene conducts electricity through it. It is the good conductor of electricity. These pure p orbitals interacts with each other, undergo partial overlapping with each other to form pi bonds. So pi bonds are formed due to partial overlapping of p orbitals. So hexagonal rings and pentagonal rings containing alternate double bonds. Due to the presence of alternate double bonds, it has aromaticity character. Buckminster fullerene has aromaticity nature due to the presence of alternate double bonds. C60 molecule contains carbon-carbon single bonds and carbon-carbon double bonds. Carbon-carbon single bond length, carbon-carbon single bond length is 1.43 picometer, 143 picometers. Carbon-carbon double bond length is 138 picometers. Here pentagonal rings and hexagonal rings. Pentagonal and hexagonal faces are arranged on the soccer ball shape. The structure of C60 molecule similar to soccer ball structure. It is a hollow sphere. Buckminster fullerene was discovered by American scientist Robert F. Curl. Robert F. Curl and H.W. Crato and Richard E. Smalley. Team of American scientists Robert F. Curl, H.W. Crato, Richard E. Smalley. Nobel Prize was awarded to them for the invention of C60 molecule. For the structure of C60 molecule, Buckminster fullerene is used in medicinal field. It is used as a potential medicine. It is used as an antibiotic to target bacterial resistant and also used for the treatment of cancer cells. Cancer treatment. The structure of Buckminster is similar to geodesic structure was discovered by American architect Buckminster. That's why this molecule is named as Buckminster fullerene. Molecular formula C60. Now we are going to discuss another allotropic form of carbon is nanotubes, carbon nanotubes. Buckminster fullerene is also crystalline allotropic form of carbon, and another allotropic form of carbon is nanotubes, carbon nanotubes, nanotubes of carbon. Generally, carbon nanotubes made up of hexagonal rings with carbon atoms. The structure of carbon nanotube is similar to single crystal layer or single hexagonal sheet of graphite or graphene. Graphene is nothing but single hexagonal crystal layer or single hexagonal crystal sheet molded or folded into a cylindrical tube. That cylindrical tube is called nanotube. That cylindrical tube is made up of hexagonal rings with carbon atoms. A single graphene sheet, hexagonal crystal sheet is folded into cylindrical tube. This tube is called as nanotube. In this nanotube, each carbon is sp2 hybridized and each carbon bonded to other 3 carbon atoms with 3 sigma bonds. Each carbon carries one unpaired electron in pure pz orbital. Each carbon has one unpaired electron in pure pz orbital. Due to the presence of free electrons, each carbon has one unpaired electron. Due to the presence of free electron, it conducts electricity. It is the good conductor of electricity like graphite. So, nanotubes are also used in electrical instruments. It is used in integrated circuits. Nanotubes are also used in electronic instruments. Nanotubes are obtained when laser rays when laser rays are allowed to fall over the graphite vapors, carbon vapors at high temperature. Nanotubes are obtained, prepared when laser rays are allowed to over the carbon vapors or graphite vapors at high temperature. Nanotubes are also used in medical field. Nanotubes used for introducing of biomolecules into tissues. Biomolecules are inserted into the nanotubes. These nanotubes have conductivity behavior. Because of conductivity behavior, this nanotube is connected to single shells. Nanotubes used for introducing of biomolecules into tissues. Nanotubes are also used for the treatment of heart problems. Injured heart tissues, injured heart tissues, injured heart tissues are repaired by using of nanotubes. These nanotubes are attached to damaged heart tissues to overcome the problems. That's why nanotubes are also used for the repairing of damaged heart tissues. Even in heart patients, that stents also, graphene stents also used in operations. So nanotubes are also used in medical field. Nanotubes are also used in water and air filters. Water and air filters. Buckminster fullerene is also used as antibiotic. It kills bacteria, it kills microorganisms. Nanotubes are also kills bacteria. Nanotubes are also kills bacteria. Now, Buckminster fullerene prepared by the heating of graphite. For example, when graphite is heated, when graphite is heated to high temperature, it changes into vapors. These vapors are undergo condensation in the atmosphere of inert gases like helium or argon gases. So Buckminster fullerene prepared when graphite vapors, when graphite is heated to high temperature, it changes to vapors. These vaporized carbon undergo condensation in the atmosphere of inert gases like argon. That resultant product is called as Buckminster fullerene. Carbon nanotube was discovered in 1991 by Japan scientist Sumio Lijima. Nanotube consists of hexagonal arrangement of covalently bonded carbon atoms. It contains hexagonal rings. Nanotube consists of hexagonal arrangement of covalently bonded carbon atoms. This structure is similar to graphene. Graphene is a single hexagonal crystal sheet, flat sheet. Graphene is the single hexagonal crystal layer, single hexagonal crystal sheet, flat sheet. But this single hexagonal crystal sheet rolled into a cylindrical tube. That cylindrical tube is called as nanotube. Nanotubes furtherly divided into two types based on the number of graphene sheets. Nanotubes are divided into two types: single-walled nanotubes, multi-walled nanotubes. Single-walled nanotubes consists of single sheet, one graphite sheet, one layer. Single-walled nanotube consists of single graphene sheet, one graphene crystal sheet. Multi-walled nanotubes are divided into two types. Multi-walled nanotubes consists of number of graphene sheets, number of hexagonal crystal sheets, multi-layers, multi-sheets are there. They are divided into two types. First one, Russian dollar structure, and second one is parchment structure. Russian dollar structure means that consists of nanotube consists of multi layers. It consists of multi graphene sheets, hexagonal crystal sheets. Parchment structure means only it consists of one graphene sheet, one hexagonal crystal sheet. That one hexagonal crystal sheet, graphene sheet, rolled into multi layers. One sheet rolled into multi layers, multi walls. This is called as parchment structure. Nanotubes also divided into two types based on the optical activity, based on the chirality, optical activity. Nanotubes are two types: chiral carbon nanotubes, achiral carbon nanotubes. Chiral carbon nanotubes are two types based on the optical rotation of plane polarized light. Right-handed carbon nanotubes and left-handed carbon nanotubes. And second one is achiral carbon nanotubes. They are learning. Amorphous allotropic forms of carbon. Allotropic forms of carbon divided into several types. The first one is coal, and second one is coke. Third one is gas carbon, and fourth one is charcoal. Sugar charcoal, animal charcoal or bone charcoal, and third one is the wood charcoal. Wood charcoal, animal charcoal, sugar charcoals are under taken in charcoals. Charcoal is furtherly divided into three types: gas carbon, coke, coal, lamp black, carbon black, all are called as amorphous allotropic forms of carbon. Generally, coal, first amorphous allotropic form of carbon is coal. Coal is obtained from earth crust. 500 million years ago, plant bodies, animal bodies are buried inside of the earth crust under high temperature and high pressure. As the result of high temperature, high pressure, vegetable matter is converted into coal. Here, atoms are converted into carbon atoms. This is called as carbonation. Carbonation takes place. Vegetable matter slowly converted into coal under high temperature, high pressure inside of the earth crust. As 500 million years ago, plant bodies, animal bodies are buried inside of the earth crust. Due to carbonation process, they are slowly converted into coal. First, wood, vegetable matter. Vegetable matter is converted into peat. Peat is the one type of coal, impure coal. Peat coal contains nearly 60% carbon. That peat coal is again converted into lignite coal. lignite coal. It nearly contains 63% carbon. Lignite under high temperature and high pressure. Lignite coal furtherly converted into bituminous coal. Bituminous coal. Bituminous coal contains nearly 70 to 75% carbon. This bituminous coal furtherly changed into anthracite coal under high temperature and high pressure. First, wood changed into peat. Peat is converted into lignite under high temperature pressure. Lignite changed into bituminous coal. Bituminous coal changed into anthracite coal. Anthracite is the pure form of coal. It contains nearly 91% carbon. Coal is used as a fuel. Coal containing impurities like sulfur impurities and nitrogen impurities, ammonia. Nitrogen and sulfur impurities are present in coal. After the removal of impurities, we will get pure form. That pure form is called as coke. Coke is the purest form of carbon. It contains a 100%, nearly 100% carbon. Nearly 100% carbon. Gas carbon is nothing but vaporized carbon. Vaporized carbon deposited on the surface of the solid. Gas carbon is the good conductor of electricity due to the mobility of free electrons. That's why gas carbon is used as electrode in dry batteries. Charcoal is nothing. Charcoal is furtherly divided into three types: sugar charcoal, animal charcoal or wood charcoal, animal charcoal or bone charcoal. Third one is the wood charcoal. Sugar charcoal means C12H22O11. When sugar is treated with concentrated sulfuric acid dehydrating agent, it removes water, it absorbs water. By the removal of water, we will get carbon residue. That carbon residue after the removal of water, that carbon residue is called as sugar charcoal. Sugar charcoal is the activated charcoal, best charcoal. It is used as an adsorbing agent. Charcoal is used as an adsorbing agent which absorbs other molecules adsorbed, deposited on the surface of the solid by physical or chemical attraction forces. So charcoal is used as an adsorbing agent. Animal charcoal or wood charcoal. Animal charcoal or wood charcoal is obtained by the incomplete combustion of bones containing calcium phosphate. So animal charcoal is obtained by the heating of bones. It is also used as a adsorbing agent. Bone charcoal is used as a adsorbing agent for the removal of impurities from sugar, colored impurities. Animal charcoal is used as an adsorbing agent. It absorbs colored impurities from the sugar. When it is added to sugarcane juice, it absorbs all the color materials. After the removal of colored impurities, that sugarcane juice is subjected to crystallization. We will get colorless crystals, sugar. So, animal charcoal is used for the removal of colored impurities from sugar. Wood charcoal is obtained from wood. When wood is taken in a glass tube and heated to high temperature, when wood is heated to high temperature, it produces wood tar and wood charcoal. So wood charcoal is obtained by the heating of wood. It is also used as adsorbing agent. It is also used as a fuel. Lamp black. Lamp black is a liquid. Lamp black is obtained by the heating of plant body in the absence of air. I mean, lamp black is obtained by the destructive distillation of plant body. Lamp black is used in the manufacturing of tires. In the manufacturing of tires. So carbon black, it is also liquid. Carbon black is obtained. Carbon black is obtained when hydrocarbons like methane burns in limited supply of oxygen. Carbon black is obtained by the incomplete combustion. I mean, methane gas or hydrocarbons burns in limited supply of oxygen. Carbon black is used as a paint, and it is also used as printing ink. So carbon black, lamp black, coal is several types. Coal is also used as a fuel like peat coal, lignite coal, bituminous coal, anthracite coal, coke, gas carbon, charcoals, all are called as amorphous allotropic forms of carbon. So amorphous allotropic forms of carbon is completed.